So let us start today's discussion. So what we have been discussing so far is the following. We have been discussing about the divergence structure in the 5-4 theory, and we derived an expression in the last class. And the expression was the following form. Okay, to follow expression as b minus b by 2 minus 1 is b plus small n minus 4. So what we did was said that every diagram, for example, we have seen two divergences in 5-4 theory. One is this divergence. This is all these diagrams are one loop, and this another one loop diagram of this one. And if D is the number of spaceline dimensions, and for every Feynman diagram, what we have is some external lines, some vertices, and there will be number of loops and internal lines, which are the propagators. Loops and internal lines we have actually eliminated from this expression, and this capital D is the degree of superficial divergence. D of superficial divergence. This we have seen. Why superficial? We shall discuss today. And if D is equal to 4, then we have seen that this expression reduces to 4 minus E. This term goes away, then we have this. So this basically tells us that any diagram which has more than whose number of external lines is more than 4. So for any Feynman diagram where this condition is satisfied, then those diagrams will converge, right? As you asked, Saurabh asked in the last lecture that what do you mean by a negative capital D? A negative capital D basically means that all your diagrams will converge. And for example, this diagram has 2 E's, so this D is capital, this is 2, and for this diagram D is 4, so D is 0, so this also diverges, so this is a logarithmic divergence. But now let's come to the question of superficial divergence. Let's get it more carefully. We are saying that for any diagram whose number of external lines is greater than 4, those diagrams will converge. So let us consider a diagram of this form. This will be something like this. So this is one vertex. Okay. Here there is no problem, as you can see that this diagram has basically, there are no loops. First of all, it has no loops. There are tree level and tree diagram. So this will have no problem, it will converge. But moreover, if you look at this diagram carefully, then you will see that there are 6 external lines. So E is 6 here, and therefore D minus 2. So you can say that this will converge. But now let's see if you put in something like this. This is also a diagram, right? For 5-4 theory. So online people are there. So if you put in a loop here, this particular diagram also has E6 and D is minus 2. This also has 6 external lines. 1, 2, 3, 4, 5, 6. This line is an internal line. Because this is a line between 2 vertices. And this also is an internal line. But the important thing is that this diagram has 6 external lines. And therefore, by this calculation, D is 4 minus 6, which is minus 2. And therefore, this diagram should be a convergent diagram. but it is not convergent because it has one loop. If you calculate this thing, this diagram is not convergent. And that is why, even though this tells you the degree of divergence and it tells you that when D is negative, the diagram should converge, it is not true always. You can cook up examples where even if the value of D is negative, the diagram is not convergent, it is divergent. And that is the reason that you call this to be the degree of superficial divergence. So now you have a theorem which we shall not prove at all. We shall just state the theorem. It's a theorem which is known as Weinberg's theorem. You may write it down. The theorem tells us that a Feynman diagram converges. A Feynman diagram converges if its degree of superficial divergence, capital D, together with the degree of divergence. A Feynman diagram converges if its degree of superficial divergence, capital D, comma, together with the degree of divergence of all its subgraphs is negative. So we say that if the degree of superficial divergence, capital D, together with the degree of divergence of all its subgraphs is negative, then you say that the particular diagram is really convergent. So that is a theorem by Weinberg, and this is the reason why you call this capital D to be the degree of, not to be the degree of divergence, rather degree of superficial divergence. And now I can derive it as I derived it yesterday, the degree of superficial divergence. Suppose your theory is 5 to the power of r. Then also you can derive a degree of superficial divergence. For 5 to the power of r theory, if there are n vertices, then at each vertex there will be r number of lines, right? Therefore, the only modification in one of the equations will be r into n, and that will be equal to number of external lines plus this. This is the only modification that you will have. Because at each vertex there will be this number of lines, some of them will be external, some of them will be internal, internal will be counted twice. So you have this equation along with the other equations that we wrote down, and then you can calculate the degree of divergence for that. And if you do that, you get a very similar expression. I will not find it here, I will just make the modification here. It will be plus n plus n. You can check this for yourself. Simple algebra 2. This will be the modified expression. And you can check for r is equal to 4 that it reduces to the previous one. Okay, for d is equal to 4, if you take this expression, for d is equal to 4, let us look at this expression and see what we get. Capital D will be 4 minus, this will be minus e, plus this will be 4 n, this is 2 r minus 4. Okay, for d is equal to 4, you have this. So let's see what happens when r is 6. That is, you have a phi-6 theory. What happens for phi-6 theory? For phi-6 theory, we'll see that the degree of superficial divergence, capital D, is basically 4 minus e, and this all this is in 4 space-time dimensions, plus n. Okay, so this is the degree of superficial divergence, And from this expression, we can immediately see that at each order, whenever when you go to higher and higher orders in perturbation theory, the vertices increase. And when n increases, you see that all the higher diagrams that come from higher order perturbation theory, all these diagrams are divergent. They are not convergent at all, and the degree of superficial divergence actually increases the more you go to higher and higher orders in perturbation theory. And therefore, this theory is completely hopeless. This is unrenormalized. You cannot tackle. We have not talked about. We have just mentioned some very elementary ideas about renormalizing.
Sir, can you repeat again why you are calling it unrenormalizable?
Yes, I will do so. See, for this phi-6 theory, the degree of superficial divergence is actually increasing with increase in the value of n. And n is what? N is the number of vertices that you have in your theory. So as you go to higher and higher orders in perturbation theory, so for example, when we do our perturbative calculations up to first order in the coupling constant, then there is how many vertices? One vertex, right?
Yes, sir.
So n is equal to 1. When you carry the calculation to second order in perturbation theory, there are two vertices. So n is equal to 2. And you can see that as you increase the order up to which you are calculating your result, for example, any scattering amplitude or whatever, the degree of superficial divergence is increasing. So the higher you go in perturbation theory, the more you will have more diagrams, and those diagrams are even more divergent. And therefore, this theory is completely hopeless. So it basically tells you that the theory is not renormalizable. So roughly, renormalizability means that even though you have infinities in your theory, but those infinities if you can tackle, or if you can make a sense out of that theory which contains infinities, then the theory is said to be renormalizable. If you cannot make sense out of those infinities, then the theory is not renormalizable. And phi-6 theory is such a theory. So let us now come to r is equal to 3 say. So for r is equal to 3, let us take this expression and we see that for r is equal to 3, this is 4 minus e minus n. So this theory, you see that as you go higher and higher in perturbation theory, as your number of vertices increases, the degree of superficial divergence decreases. And therefore, this theory is renormalizable, and it is not only renormalizable, it is called super renormalizable. Phi cube theory is called super renormalizable. Phi 4 theory is also renormalizable. Phi 4 theory, we have seen that d is basically 4 minus e. It does not depend on the vertex at all. So phi 4 theory, it turns out that it's a renormalizable theory. This, as you increase or as you go higher in perturbation theory, higher orders in perturbation theory, this theory is completely is very nice. It's called super normalizable because the number of divergent diagrams that you have at higher orders in perturbation theory is very less. Because, for example, if you for pi cube theory, if you have say a diagram where there are say two external legs, so this is 2. And therefore, you know that from third order in perturbation theory, there are no divergent diagrams. Even though there may be loops or whatever, but those diagrams are not divergent from third order in perturbation theory. So it is a very nice theory, but that is not true for phi 4 theory, because phi 4 theory is independent of n. So every order in perturbation theory will have divergent diagrams. So there will be loops and those diagrams will be divergent. But it turns out that you can control those divergence in a nice way, and therefore the theory is renormalized.
Sir,
So,
that means after phi to the power 4 theory, no theory is renormalizable.
right.
Okay.
At least in this class of theories.
Okay.
Huh? D equal to 4 space-time. This is in D is equal to 4. In D is equal to 4 space-time dimensions. But it may be denormalizable if you tweak this small d. Then it will be normalized. For example, if you take Fix theory in some higher dimensions, then you have to just check what this value of capital D is. Okay, so this is what I wanted to mention about 5 to the power of 4 theory. And another thing that we should know in 5 to the power of 4 theory is the following, that this theory at one loop, these are the primitive divergence diagrams that you have in this theory. So these are called primitive divergent diagrams. For 5 to the power of 4. So this one and this one. And all other diagrams we can construct basically from these primitive divergent diagrams for 5 to the power of 4. So, what are the subgraphs? What are the subgraphs? For example, here you can have many diagrams, for example. Remember this diagram? This was the. Did we discuss this? Yes, we discussed this. This Saturn diagram, or sunset or sunrise kind of a diagram. Then you can have the diagram. You can go on constructing diagrams. So these are basically two loops. This is two loops. These are two loops. At one loop, you know that these are the only diagrams. Then you can go on constructing. One thing that you can do is find out what are the possible two loop diagrams in 5 you can try and find it. So this is one. This is another one. I think there are two more. Maybe it's 90. This one. You can go and find the diagrams at third order. What are the third order diagrams? So far so good with 5 to the power 4 theory. So today what we shall do, we shall start another theory which involves fermions. So let us start that. So let us write down the interaction Lagrangian density is the complete constant of the theory. So we have seen what Dirac fields are, we have seen what real scalar fields are. You can construct there can be other forms of the Lagrangian, for example, Lagrangian density. For example, you can work with the theory of this form. By the way, this is in the interaction picture, therefore all these fields are basically fields in the interaction picture, and therefore they evolve by the free part of the Hamiltonian. You can have theories of this form. So this is the coupling constant, this is the complex scalar, this is the real scalar. But what we shall do is, this is a very simple theory, but you can do the same things, whatever you can do in this theory, you can do the same things here also. This theory has the extra complication that this is a Dirac fermionic field. This theory does not have that complication, all these fields are bosonic fields. So simplification that you have in this theory has some additional complications. And what we want to look at is, we want to look at process, for example, you know what are the quantas of this Dirac field? Okay. This is what we want to look at. We can write in this way also, or whatever. When you are writing positrons, it means this way. Okay. So we want to look at a decay process. So a scalar particle, the quanta of a scalar field, the real scalar field. This is charge neutral because real scalar field has quanta which has no charge. It decays into an electron-positron field. Okay. The decay of a scalar particle, and our aim is to basically calculate the decay rate. What is the lifetime of this process? But for that, we have to calculate the amplitude, the probability amplitude for this process, and you know what it is. Basically, some matrix element. That matrix element electron has momentum, free momentum p vector, and spin is spin s. Positron momentum p prime prime. Scalar particle. We want to calculate this. This is our aim. Okay. So here we can write it like this. Later on, I will tell you. This is the S matrix, and we want to calculate this. And you know that the S matrix basically time order, or it can be exponential of the IT. What is the Hamiltonian density? Hamiltonian density will be plus. So you will get a plus from here. Therefore, this is nothing but e to the power of minus I each bar. The sign will change for the Hamiltonian density. This is basically, you can write this down as d4x hix. Limits are from once again from minus infinity plus infinity. Therefore, put in the form of hix, the Hamiltonian density, shall get minus I g h bar integral this interaction is normal order because we want it to be normal order so that all the creation of operators are of the left of the integration operators. So this is your S matrix, and what we need to do is put this S matrix here, calculate this matrix. Is the problem clear? I think this is clear, it's simple, and so now we can expand as before. We have done this earlier also for 5-4 theory. We have done it. So if we expand this, if we get identity operator first term, then we should get ig by h bar integral for x normal order, then we will have plus 1 by 2 factorial minus 9 square e4x e4y time order, time ordering, then we have and then you have a shorthand way of writing this. It's not that difficult. So replace x by 1 plus dot dot dot. Okay. Is this clear?
Yes.
Is it clear for the online people?
Yes, sir.
Okay.
Yes, Professor.
Good. Are you okay with it? It's fine. Very good. Okay. Now let us concentrate on this part, and we'll see that the first term, if I put here, what will be this? If you put identity in the first term, you put s over here, the first term will be 1. So what will be the value of that? It should be delta k minus this, but one thing you should in your mind, that these are different particles, right? So this term is not there, and it is 0, and it is not interesting also. It is not interesting because it will not contribute to the lifetime. So just forget about that term, identity term. So the next term, so the term that is important here will be so let me call this term as S1, this one. What is S1? S1 is minus I H bar By the way, this kind of interaction is sometimes called, is known as Yukawa interaction. Yukawa interaction, or this is also sometimes known as scalar QED, scalar quantum electrodynamics. Electrodynamics, because you can understand, because there are electrons and positrons involved here, and it is scalar electrodynamics because there is no gauge field here. Instead of gauge field, you have a real scalar. So this is called scalar QED, or so this sort of a toy model, or sometimes it is also known as Yukawa interaction. This is also a Yukawa interaction, but this is also a toy model of scalar QED. So it is better to tell this as Yukawa and this as scalar. So this is all are scalars, scalar QED kind of a toy kind of interaction. It is up to you what you want to call. So you can see the side of the codes. Now let us concentrate on this matrix element.
Complex scale if you want to calculate for the first time, we cannot say that it is zero as here the particles are different. This boson are different, but in that case both are boson.
No, the particles are different. Okay.
Quantum numbers are
Not quantum number. See, this the quanta of this particle is this d with momentum k, but the quanta is b. It is up to me what I call b, a, whatever. You can call this as you. Well, you can call this. See, this is the quanta of this particle. Okay? It's up to you. And the quanta of this particle, of this field, the quanta of this field, we know that these are electron and positron. But the quanta of this complex scalar field is not this. It's something else. Or you can say, so the quanta of this field is this, quanta of this field is this. It is completely different. Therefore, that term will also be zero. Because the quanta of the fields are different. Now, let us concentrate on this matrix element. So, if you look at this matrix element, before calculating anything, we should look at the structure of this matrix element and see that there are so there are three particles and here are three fields. Okay? Therefore, it is fine. This will contribute. And once you know that if you calculate this, then you will get something out of it because there are three particles, there are three fields. This field corresponds to this particle, and these two fields corresponds to these two particles, and therefore there will be one at least one term here which will annihilate this particle, it give you a vacuum on this side, and these two fields will annihilate the particles here, give you vacuum on the brass side, and therefore that will contribute. So this is at first order in perturbation, right? This is the first order in perturbation. We shall calculate this explicitly, this term. Let us look at the second order term. Okay? Second order term. Do you think this term will contribute to this matrix element? Do you think so? The second order term. Why not?
second order just for phi real scale phi x, that is phi x phi y. So it will either increase this it will never annihilate two particles here and create two particles here.
Right. Good. Good. This is your argument is correct, but you are saying that there are two files. There is only one particle. So once it will annihilate, then there will be nothing immediate vacuum. Again, it will annihilate. It will be zero. That is a way of understanding. Other way of understanding, you apply Wick's theorem. You apply Wick's theorem. The first term will be just this. There are three particles, six operators. Then you apply one contraction. This with this. So two are gone, two operators are contracted gone, four operators are there. Four, three particles, zero. Contract two. So four are gone, two remains. Two will annihilate. So three particles, two, one will remain. So orthogonality zero. Three, everything is out, not is orthogonal. Particles will remain, so this is orthogonal. So this term will not have any contribution at to this matrix element. What about the third order term? This is something interesting. If you write down third order term, Will it contribute or not? Without calculating. See, you are not calculating, no calculations. I have not done anything. Can you tell me that will expand this and take the third order, keep terms of third order, will it contribute to this matrix element? Third order, how many operators are there? Huh? 9. Very good. 9.
9
So what will
operators.
huh?
9 operators.
Yes. So 9 operators. So will it contribute?
Yes.
Yes. Why?
Sir, because if you contract 2 to 6 are contract.
6 are gone. So 3 will remain. So they will contribute. And there will be many diagrams. There will be many Feynman diagrams, interesting Feynman diagrams that you will get at this order. And what will it do? It will basically, when you calculate up to third order, it is basically a correction to this first order result. It's a correction. It should be a correction to that first order result. So that is what it should be. So as we go higher and higher in perturbation theory, higher orders in perturbation theory, you will calculate corrections to the leading order result. So this term will give you the leading order result, and subsequently you will get corrections. So let us now calculate the leading order term. So this we call as SA5 or A1. A1 is nothing but minus IG by each plot equal x. So this is what we need to calculate. And before calculating this, we shall divide this calculation into steps. What we shall do is we shall just look at this thing, and for that we shall write phi x to be equal to phi plus x plus phi minus x. So the convention is, when I write phi plus, I also use this convention earlier. Whenever it is plus, it means that this is the annihilation part, this is the creation. We have psi x, this is psi plus x plus psi minus x. So this is the annihilation part. So this is the electron annihilation. This is what? This is a creation. Creation of what? Creation of positron. Now we have psi bar x, which is once again psi bar so here it was annihilation of electron. So psi bar minus is basically creation of electron. This was creation of positron. Psi bar plus x, plus is always annihilation, and this is the annihilation of positron. So these are the three decompositions that we have taken, and we just need to write out this product. This is psi bar plus psi bar minus. Then we have psi plus okay. straightforward multiplication. We will have 8 terms. So psi plus psi bar minus, multiply this with psi bar plus psi bar minus plus psi bar plus minus plus psi bar minus. And then there will be 4 more terms. You can write it explicitly. But what is important out of these terms, just consider this term. If you put it over here, then what will happen? 5 plus will annihilate this, so you will get 0. So you will get vacuum. And then psi plus, what does it do? It annihilates an electron, so that will be 0. So this term is 0. No contribution. In the same way, just look at all those terms, everything will be 0 excepting this term. Except this term. Phi plus, it annihilates this, get a vacuum. Psi minus, what does it do? Creates a positron. Psi bar minus creates an electron on the right hand side, on the K side. The brass side here sitting. So out of these 8 terms, there were 8 terms, only one term, this one, we contribute. We need to calculate that term. So we shall do this calculation later. But for the time being, just look at this theory and you may finish up the calculation before I do it on the board. Yourself, you may wait for next Wednesday. Tomorrow I shall not be able to take the class. So tomorrow I have a problem and Monday is a holiday. Right? So we'll meet again on Wednesday. Wednesday is what? Wednesday is 31st. Today is 24. So we meet on Wednesday, and Wednesday we shall take this term, we shall calculate it, at least the first order term. So if you have any questions, you may ask at this point. Our aim here from now on is actually why we are doing this theory is we shall try to see how you can calculate a matrix element, and then once you get the matrix element, calculation of the lifetime is trivial. You can do it yourself. That is not a problem. But our main goal of studying this theory is to derive the Feynman rules of this theory. The Feynman rules for the fermions. We have the rules for the scalar field theory. We have looked at the propagator for the fermion and the photon field, the gauge field, but we need to find out the other rules also for the fermionic field. Once we have those rules, we just need one more rule for the photon field, but that we shall assume for the time being, and then we shall start QED, doing QED. So we shall not look into this theory very much because this is a toy model kind of a theory. We shall straight away go to quantum electrodynamics and study some processes in QED. That is our aim.
Are you going to do normalization?
No. At least for this course. Okay, so I'm stopping the online thing now. If you don't have any questions, then we can stop.